canceled, buddy.
Oh my God.
Okay, so this is number 2 from the Fall 25 exam, and it is a device modeling problem. So these problems always come with a paragraph. It tells us that a device shown in figure 1 can be modeled as a voltage source in series with a resistor. So that is your important key word that we will be basing our solution around. So I'm going to highlight that. So that's super important. And then it says, use the data in figure 2 to find the Thevenin equivalent model of the device, draw it clearly, and label the model of the device. All right, so that's part A. Part B is going to have us insert that device into the circuit and find a Norton equivalent. But we'll cross that bridge when we get there. First, let's look at the device itself. So we are given 2 terminals, A and B, and we are told that the device can be modeled by a Thevenin equivalent, essentially, or a voltage source in series with a resistor. And we are going to name those V Thevenin and R Thevenin. We are given a current to be entering the A terminal called ID and a voltage across the 2 terminals, VD. And we are given 2 points in our graph for VD, ID, and VD. We're given 2 points. Our first is 8 milliamps. Our second point is 0 milliamps at 10 volts. Be careful, that is not 0 volts, 10 volts. So those are our 2 points. And we're just gonna keep those to the side for now. They're gonna come in handy later. But before we can actually use them, we need to derive a equation for our device model, which naturally, given that it is a voltage source in series with the resistance, a KVL is going to be our best bet for that. So doing a KVL around our device model results in the following equation. Negative V Thevenin minus ID times R Thevenin plus VD equal to 0. And remember, it's minus ID times R Thevenin, just to really emphasize it, because we have current entering the positive terminal.
0 and 10 volts.
From the given graph, yeah. So at 0 milliamps, the voltage VD is 10 volts.
Oh shit, my bad. I thought it was 0, 0, 0.
Yeah, no, you gotta be careful. It's not 0. It is 10.
The resistors always, the current always enters the voltage.
Yeah, exactly. Okay, so now that we have our equation, we are just going to take these 2 points for ID and VD and plug them into our KVL. That will give us a system of 2 equations with 2 unknowns, V Thevenin and R Thevenin. So let's do that. Our first equation is going to be negative V Thevenin minus 8 milliamps times R Thevenin plus 24 volts. Our second equation is negative V Thevenin minus 0, because now we're at 0 milliamps, plus 10 volts. Sorry, and both of these are equal to 0. So using those 2 equations, we can solve for our 2 unknowns. In fact, using the second equation, we can very easily see that V Thevenin is just going to be 10 volts. And then you can use your other equation to solve for R Thevenin. Mm-hmm.
Do we really have to do the KVL? Because we already like know it's gonna be 10
Yeah, I mean, because if the current is 0, how are you going to know that V Thevenin is equal to VD without writing out that KVL? I mean, granted, you can see that if there's 0 current going through this resistor, there's 0 volts across it, right? So this voltage has to be equal to that. That's a way you can think about it. But then again, you still have to take that 10 volts and solve for R Thevenin. Unless, do you have some way you could do it that you're thinking? 'Cause there might be a way.
You can find the voltage change and so we know that the voltage went from 10 to like 24, right?
Yeah.
So we can find the voltage change and we can just do V over I.
Yeah, so taking the slope of the line?
Yeah.
Yeah, that's a valid approach too. And I mean that's how this would work, right? Because we know the equation of a line is y equals mx plus b, right? Well, here y is our VD, that's the vertical axis that we're given, and our x is ID. And so if we were to take this equation and solve for VD, we get VD is equal to V Thevenin plus ID times R Thevenin, right? So this is our independent variable, x. This is our slope. And then this is our B, which is our y-intercept. So here, our y-intercept is 10 volts, right? So as a result, V Thevenin is 10 volts. That's our y-intercept, that's our B. Our M, if we find the slope, well, our slope is going to be R Thevenin. So if you took the slope of this line, which is 24 volts over 8 milliamps, you get 3 kiloohms. So yeah, that's another way of approaching this problem. You still have to take your KVL equation and then format it into the equation of a straight line, because a lot of times it works out to where, you know, maybe instead of a plus ID times R Thevenin, it's minus ID times R Thevenin. So then when you find your slope, you then have to flip the sign. But you have to have your KVL to see that. But here it works out pretty nicely. Just make sure all is good. 16, 24. It's not 24. Yeah. It's 14. You're right. You take the difference. Yeah, that's my bad. You take 24 minus 10 volts over 8 minus 0 milliamps. And then you get, 14 over 8, which is 1.75 kiloohms. So now our device model is going to be this. All right, and that's our answer for part A. Now, part B wants us to plug it into this circuit and find the Norton equivalent. So let's do that. Get our battery. Listens. Now, as a side note, whenever you are plugging your devices into your circuit, you have to pay very close attention to where the terminals are. So it has terminal A being on the top of the device where it's inserted into the circuit, which means that this side needs to be on the top half of where we insert it into the circuit. So that's why I drew the battery given that polarity. And we just insert our values for our device and then connect it to the rest of the circuit. And 4 VB. Resistor. All right, and it wants us to find the Norton equivalent as seen by the battery on the right side. So I'm going to remove that battery and replace it with 2 terminals. And then that is where we need to find our open circuit voltage. So, 3IA, 4 VB, 4 VB, 5 kilo ohms, 7 kilo ohms. And then VB is that voltage, and IA is this current. Okay, and then how would y'all like to solve this circuit? Nodal analysis. Yeah, VB. Yeah, I like nodal analysis. Oh, give me just a second. I'm getting a phone call and it's probably regarding the pizza. So let me just make sure. Let me make sure everything's good. Okay. Sorry about that.
So was it regarding the pizza?
It was. It'll be here momentarily.
So was it?
Yeah.
So was it?
All right, so yeah, we're gonna do nodal analysis. Since VB is defined to be the voltage across this dependent current source with the negative terminal being at the same node as our ground, we can call the top node VB. And so now we just need to write our equation for VB, which is VB minus 10 volts over 1.75 kilo ohm plus or minus 3IA plus VB minus 4 VB over 5 kilo ohms equals 0. And now we just need an equation for IA, which we already have the equation for IA through Ohm's law, which is negative 3 VB over 5 kilo ohms. I just took that term and brought it there. And that is our IA. I just combined the VB minus 4 VB into a negative 3 VB over 5 kilo ohms, because that is the same as this current. Because as we know, there's zero current going through that open circuit. Which means we can get rid of this resistor because there's zero voltage across it. And so then we can plug these two equations into our calculator. And we will get VB equals 3.23 volts. IA is equal to negative 1.94 milliamps. And VOC can also be observed to be the same voltage as the voltage across that 5 kilo ohm resistor, right? So VOC is IA times 5 kilo ohms, which is negative 9.68 volts. Okay, that's our VOC. Any questions? Okay, now we need to find R Thevenin. And there's some dependent sources, unfortunately. So we are going to have to use everyone's favorite test source.
And so what's the time limit on the test?
Huh?
What's the time limit on the
Probably an hour and a half.
Right.
This one had 5 questions.
Right. Right.
Oh, for sure, confirmed 4? Okay.
And he also said he doesn't know the time.
He doesn't know how much time it's going to be?
It's probably gonna be less than that.
Less than an hour and a half?
Less than an
Hey,
hour.
if you got an hour and a half for how many 5?
Well, all exams were an hour and a half for us.
That's what he said.
Was your exam 1 an hour and a half?
Yeah, but that
Two
was
was
also
cut off half.
Oh, yeah, true. True.
And they're probably not gonna make us do like a big match like that if the way that they're.
Yeah, and also, like, just because it's only 5 questions, like, our exam 3 was 4 questions, and we had 2 hours on it because the questions were so hard. So I wouldn't say
I
that
think we're gonna get 2 switches though.
exactly. So I would say the time is more proportional on the difficulty of the exam and not the quantity of questions. So, yeah.
I have a question. If we do ISC, would that give us I naught?
Yes.
Like ISC is equals to I naught?
Yes.
Okay.
That would do that.
Pretty long.
Nothing wrong with it. It might even be easier. Sometimes it is easier to short out your terminals. I always feel more comfortable with VOC. So I always find that in source transformation. All right, so I'm going to do test source. So I'm going to redraw our circuit. Correct, yes. Now you need to bring that resistor back into things. And remember, with test source, we're going to short out all voltage sources and open all current sources, but there's no current sources. But that 10 volt voltage source from our device model is now going to be shorted. That's 4 VB, 3 IA, 5 kilo ohms. And that was what, 7 kilo ohms? Yeah. 7 kilo ohms. This is the current that we are trying to solve for, IT. And of course, we still have our IA and our VB. And this is our 1 volt. So, let's use no voltage method again. Yeah, good with that?
The 1.75, doesn't it just short as well? Because you got 2 terminals on top, that A and B.
No, the voltage source is going to get shorted out.
I know, but you know you have how you have like your A on the top and
Mhm.
B. 2 like terminals.
Yeah, for the device?
Yeah. And they're open.
So this is kind of what we're doing here. A, B, we're taking it and stretching it out, and we're connecting it into the circuit. So it's not open circuit anymore.
Oh. So you're gonna have to like have the A and B on the like the A on the top.
Yes. And actually the resistors on top, right? So it should be right there. But yeah, you're essentially taking that device model, making it vertical, and plugging it into the circuit where the device is. And okay, so here we're gonna do nodal analysis. And we can say that this node is VB. We can just call this node VA. And then our constraint equation is going to be VB minus.
Can that VA node technically be like 3VB?
Yes.
Or negative 3
Negative 3.
Negative 3VB, yeah. And that can be observed through your constraint equation, right? That's also a valid approach too. You can just call it negative 3VB because it's the same variable. But when you do your nodal analysis, you're still going to have this current, this current, this current, and that current. But yeah. Either approach is fine. And so then your nodal equation is going to be VB over 1.75 kiloohms minus 3IA plus VA over 5 kiloohms plus VA minus 1 volt over 7 kiloohms equals 0. And then your IA is just going to be VA over 5 kiloohms. Uh-oh. Ah. Ooh. All right, we're back. Okay, so you solve those equations. Remember, what we're looking for is IT, but we can safely bet that we're going to need VB, VA, and IA in order to be able to solve for it. At least one of them, right? And I don't actually have the values for it on what I have already. But let's write our equation for IT. And here, IT conveniently goes through a resistor. So we can use a very simple Ohm's law expression to represent the current IT. You just take the voltage on the starting side, which is 1 volt. Because this node right here is 1 volt, right? And then you subtract it from whatever you find for VA, and then divide that by 7 kiloohms. And once you do that, you will get 0.188 milliamps. And so R Thevenin is equal to 1 volt over 0.188 milliamps, which is 5.306 kiloohms. Okay, now last step before we draw our Thevenin or Norton equivalent is to find our Norton current, which is just going to be V Thevenin, negative 9.68 volts, divided by 5.306 kiloohms, which is going to be negative 1.824 milliamps. And we have two terminals that I'm going to name them arbitrarily as C and D because we already have A and B. And then we're just going to write our values. Negative 1.824 milliamps and 5.306 kiloohms. And that's your answer. Of course. Yeah. Zoom in on which one? This good?
It takes too long.
Haven't heard that one.
Expecting to write like C and D or like
Yeah. They might take a point off. I don't know. always label your terminals. Just be safe. And don't reuse terminal labels that they already give you, like A and B. But what I can say for certain is if they ask you to find Thevenin or Norton equivalents with respect to two terminals that they do label for you already, then at that point you will 100% lose points if you don't label the terminals at the end. Same reason you have to label your terminals A and B here, because the device model gives you terminals A and B. Okay. Huh?
Are we gonna be continuing this worksheet for like the actual belief thing?
For the
Or are we doing a new one?
For the start, yeah. I'm gonna get through the rest of this old exam,
And then we'll do another.
and then I have another packet prepared.